Welcome to Free Learning Academy. Let's simplify thread states and lifecycle. When we talk about threads, we already know from the previous topics that a thread is the smallest unit of execution inside a process. We also discuss how threads help achieve better performance and responsiveness by allowing multiple tasks to run within the same process. Now it is time to understand what actually happens to a thread from the moment it is created until it finishes its work. This journey is what we call the thread life cycle, and the different situations a thread can be in during this journey are known as thread states. To make this easy to visualize, think of a thread as a worker in an office. That worker does not work non-stop from morning to evening. Sometimes the worker is ready to work, sometimes actively working, sometimes waiting for instructions, and eventually the worker leaves for the day. A thread behaves in a very similar way inside the operating system. Let us start from the beginning. When a program creates a thread, the thread enters what we commonly call the new state. At this point, the thread exists, but it has not started executing yet. Memory is allocated for it, and the operating system knows that this thread is supposed to run at some point. However, it is not yet competing for CPU time. You can imagine this as a worker who has been hired but has not yet been assigned a desk or given tasks to perform. Once the thread is ready to execute, it moves into the ready state. In this state, the thread has everything it needs to run except one thing, the CPU. The thread is fully prepared, its instructions are loaded, and it is waiting in a queue for the scheduler to pick it. This is an important point. Being in the ready state does not mean the thread is running. It simply means the thread can run as soon as the CPU becomes available. Many threads can be in the ready state at the same time, all waiting patiently for their turn. To understand this better, imagine a single core CPU. Only one thread can actually run at any given instant. If 10 threads are ready, 9 of them must wait. They are not blocked or stopped. They are simply waiting for the scheduler to say, "You are next." This idea connects directly with concepts you will study later in thread scheduling and CPU scheduling. When the scheduler selects a thread from the ready queue, the thread enters a running state. This is the moment when the thread is actually executing instructions on the CPU. Its code is being processed, calculations are happening, and progress is being made. From the outside, this feels like real work is happening because it is. However, a thread does not stay in the running state forever. There are several reasons why it might leave this state. One common reason is preemption. If the operating system is using preemptive scheduling, the CPU may be taken away from the thread after a certain time slice. In that case, the thread goes back to the ready state, not because something went wrong, but because the OS wants to give other threads a fair chance to run. Another reason a thread may leave the running state is that it needs something that is not immediately available. This brings us to the blocked or waiting state. A thread enters this state when it cannot continue execution until some event occurs. For example, a thread might request data from a disk, wait for user input, or wait for a log to be released by another thread. Consider a simple example of a music player application. One thread is responsible for playing audio, and another thread handles user input like pause or next song. If the audio thread reaches a point where it needs to read the next chunk of the song from disk and the data is not yet in memory, the thread cannot continue. Instead of wasting CPU time, the operating system moves this thread into the blocked state. While it is blocked, the CPU is free to run other threads. This is a key idea in operating systems. A block thread is not competing for the CPU at all. It is essentially saying, I cannot do anything right now, so wake me up when the thing I am waiting for is ready. Once the event occurs, such as disk input completing or a log becoming available, the thread is moved back to the ready state. From there, it waits again for the scheduler to assign CPU time. In some systems, you may also hear about a timed waiting state. This is a variation of the waiting state where the thread waits for a specific amount of time. For example, a thread may call a sleep function to pause itself for 2 seconds. During this time, it is not runnable. After the time expires, the thread automatically moves back to the ready state. This is commonly used in applications that need periodic actions, such as checking for updates every few seconds. Eventually, every thread reaches the end of its life. When a thread finishes executing its instructions or is explicitly terminated, it enters the terminated state. In this state, the thread is no longer active. The operating system cleans up its resources, such as its stack and thread control information. After this point, the thread cannot be scheduled again. It is effectively gone. It is important to note that the life cycle we just discussed is logical, not physical. The operating system does not always label states exactly the same way internally. Some systems merge states or use different names. However, the core idea remains consistent across operating systems. A thread is created, becomes ready, runs, may wait, and eventually terminates. Now, it helps to pause for a moment and compare thread states with the process states we discussed earlier in the process management module. At a high level, they look very similar. Processes also move through states like new, ready, running, waiting, and terminated. This similarity is not a coincidence. A thread is often called a lightweight process, so its life cycle naturally mirrors that of a process. The key difference lies in what is being managed. When a process moves between states, the operating system is dealing with separate address spaces, separate resources, and heavier context switches. When a thread moves between states, it stays within the same process and shares memory, files, and other resources with sibling threads. For example, when a process goes into a waiting state, the entire process stops progressing. But when a single thread goes into a waiting state, other threads of the same process can still continue running. This is why multi-threaded applications feel faster and more responsive than multi-process designs for the same task. Understanding thread states also helps explain common issues in multi-threaded programs, which we will discuss later. If many threads are stuck in the block state waiting for the same resource, performance can drop. If threads are frequently moved between running and ready states, context switching overhead can increase. These ideas will become very important when we study race conditions, deadlocks, and thread scheduling. To summarize in simple terms, the thread lifecycle describes the different stages a thread goes through during its existence. A thread starts its life being created, waits in the ready state until it gets CPU time, runs when it is scheduled, may block if it has to wait for something, and finally terminates when its work is done. These state transitions are managed entirely by the operating system, allowing multiple threads to share the CPU efficiently and smoothly. By understanding thread states now, you are building a strong foundation for the next topics in this module, especially user level versus kernel level threads and thread scheduling. Everything we discuss next will build directly on this idea of how threads move through their life cycle inside the operating system. That is it for this video. See you in the next one.